In this sandbox, we'll play with trig and algebra. Here's the problem statement. We're going to assume an angle theta provides that the difference of cosecant of that angle and secant of that angle is exactly this quotient of the square root of 13 and 6. The problem is then, what is the difference of cotangent of that angle and tangent of that angle? The result is very nice. So, if you're adventurous, give that a try. If you'd like some hints, I have hints in two forms. First, I'm going to provide you with the tools that are necessary to work the problem. And then after that, I'll go in 4 parts, step by step, on how to work the problem. All right, so first off are the tools necessary. As mentioned, this sandbox is a play on algebra and trig. We're looking for them to interact. On the algebra side, we need to be able to square terms. The terms are either going to be a single term or 2 terms, binomials. And then also, you'll want to be able to solve quadratic equations. So basic algebra. On the trig side, we have the Pythagorean identity, the form stated with cosine and sine. We'll need the 2 quotient identities to swap out tangent and cotangent for sines and cosines. Same thing on cosecant and secant, use reciprocal identities. And then the key in working the problem are going to be these double angle identities for cosine and for sine. Okay, so if that is enough to get the job done for you, awesome. If not, and you'd like some step-by-step, let's dive into that. So first part. First part is going to be looking at our objective, the difference of cotangent and tangent, and coming up with a recasting, stating it in a different way. And to get going, we'll use the quotient identities to swap out cotan and tangent in terms of sine and cosine. That'll still yield 2 different terms, the difference of, and since they're going to be stated as fractions or quotients, find a common denominator of those 2 terms and state the difference as a single quotient. Very good. Now look in the top and the bottom, and you want to multiply each by 2. The effect here is that you're going to be multiplying the entire quotient by 1. Important point there is that you don't change the value. Next, now that we've multiplied the top and bottom by 2, you can look at the denominator and note that you have a double angle identity for sine. And then in the top, you'll have a double angle identity for cosine. Be careful to leave the 2 out in front. All right, so this form here is now our updated goal, and this is what we're going to want to find the value of. Then let's go and look at the given information and start doing the same thing, working with it and seeing what we can produce. So, since we have cosecant and secant, let's first use the reciprocal identities to restate this difference in terms of sines and cosines. Like before, we have a difference of 2 quotients combine as a single quotient. Next, take both sides and raise each side to the power 2. Okay, that's part 2. Moving on to part 3. Take the last line that we had in part 2 and multiply both sides by sine squared cosine squared. Sine squared times cosine squared is the same thing as the product of sine and cosine quantity squared. Let's introduce a 2 inside the parentheses. That means that when we apply the power 2 to 2, we're going to get a 4 on the outside. To make sure that we're not changing the value, let's divide by 4 as well. Note that inside the parentheses is an expression which is the same thing as sine of 2 theta. That's being quantity squared, so we get sine squared 2 theta. Lastly, we want to take this expression and turn it into 0, which means that we want to collect all terms on one side. Thus, we have here a quadratic expression in sine of 2 theta. Let's move on to part 4. So with that, use the quadratic formula to figure out what sine of 2 theta is. Here I've stated the quadratic formula for you. Recall that sine must take values between -1 and +1, so that when you look at the two quantities produced here, you're able to eliminate either the plus or the minus and just get one single solution. Write out that single solution. It's a nice expression. Go back and think about the Pythagorean identity. It's really the Pythagorean theorem, where the Pythagorean theorem applies to a right triangle. If you have an angle theta, then the adjacent with a hypotenuse 1 is cosine of the angle, and the opposite is sine of that angle. And then you can use that if you are provided with the opposite side and assume that you have a hypotenuse of 1, you can solve for the adjacent side. However, remember that cosine produces both positive and negative values, so be careful there. Then go back and look at part 1, and you see that we recast cosine theta minus tan theta as a different expression, a single term. Look at that, plug in, and you have found your answer. Nice job, everyone.